Okay, so welcome to week eight's problem solving session. So today we'll first solve some problems related to week eight's assignment, and then we'll look at this year's week seven assignment. Okay, let's first. Okay, is this recording? Yeah, the recording is on. Okay, so let's first quickly recap what we saw in this week. So in this week first, so last week we had started the proof of this theorem by Rasbarov, Allen, and Bopanna about lower bounds for monotone circuits. Okay, so first we finished that proof, and then we saw a proof of this theorem by Rasbarov-Smolensky, which says that for any primes p not equals to q, the function mod p is not in the class AC0Q. So the function mod p is defined as follows. It's 1 if the sum of I in 1 to n xi is not equals to 0 mod p and 0 otherwise. Okay, and the class AC0Q is the class of all languages recognized by circuits of cir- circuit families of poly size and constant depth with unbounded fan-in and OR gates as well as NOT gates and mod Q gates. So AC0Q is almost like AC0, except that now we allow gates mod Q. And let's quickly look at the proof outline of this theorem. So in the class, we only saw proof of a special case of the theorem where MP equals 2 and Q equals 3. So when P is Q, mod P is just parity. And so in that case, the theorem is just parity is not contained in AC03. And to show this, what we did was the following. We showed that for every AC03 circuit C of small size, there exists a low degree polynomial PC that approximates it. That is, PC of x is CS x for most x is 0, 1 to the n. Then we show that every low degree polynomial disagrees with parity for a lot of x in 0, 1 to the n. So there exists a low degree polynomial that approximates a small circuit, but not parity. And so parity cannot be computed by a small circuit, small AC03 circuit. Okay, so this was the very high level outline of the proof. So now let's look at some of the problems related to this week's content. Okay, let me add a page. Okay, the first problem is show that uh, can be represented by a multilinear polynomial. So in the class, we saw how to construct approximate polynomials for circuits. It, and we also briefly touched upon how you can construct polynomials that capture a function exactly. So what we'll show over here is, in fact, there exists a special type of polynomials that capture functions exactly, and these polynomials are multilinear. So let me first define a multilinear polynomial. So a polynomial P is said to be multilinear uh, the degree of every xi, every monomial of p is at most 1. So for example, x1, x2 plus x3, x4, x5 is a multilinear polynomial because the degree of every variable is 1, but x1 square plus x2, x3 is not a multilinear polynomial because degree of x1 is 2 in this polynomial. Okay, yeah. So this is a multilinear polynomial, and now let's see how every function can be represented by a multilinear polynomial. So consider this polynomial defined as sum over all b in 0, comma 1 to the n such that f of b is 1, uh, product over such that pi is 1. Okay, let me do pi 0 first. 1 minus xi times product I in n. Things. So this is the polynomial, and what we'll show is that this polynomial represents f. And to do this, we will show the following two claims. The first claim is okay. Let me just do it with one claim only instead of two. So for all a 0, 1 to the n, f of a equals p of a. So fix an a such that f of a equals 1, then the claim is that uh, that product. Okay, so f of a equals 1, and therefore corresponding to f of a, there is a term over here, right? So there is a term over here which looks like this. Okay, so when I plug in ai over here, what do I get? So notice that whenever in the term corresponding to I plug in a, I get 1. Why? Because whenever ai is 0, 1 minus xi would become 1 minus ai, which is 1 minus 0, which is 1. And whenever ai is 1, xi would be ai, which is 1, right? So this entire product would be 1. So then product I in n ai is equal to 0, 1 minus ai is a summand. Okay, in PA, and this summand is non-zero. Further, okay, now I'm claiming that this is the only non-zero summand. Why? Because let's look at this for some bi not equals to ai, right? In that case, there must exist in I such that bi and ai are different. So suppose that bi is 0, but ai is 1, in which case when I plug ai over here, I would get 1 minus 1 equals to 0. If bi were 1, but ai were 0, whenever I plug ai over here, I would get 0, right? So basically, this is 1 if and only if I plug in b, right? So when f of a equals 1, there exists someone which is 1, but all the other summonds are 0. And so p of a equals 1. Uh, okay, so this proves the claim when f of a equals 1. Now we also need to look at a such that f of a is 0, right? So fix and a such that, okay, let me put this in a new paragraph. The proof is analogous is not a summand in P. So all summonds are, yeah, so in this case P of A is 0. So we are shown that when f of A equals 1, P of A is 1. When f of A is 0, P of A is 0, and so we are done. Right. So this proved the claim. Okay. So now let's look at a generalization of this state problem. Oh, by the way, I forgot the multilinear part. Yeah. So we also needed to prove that we need to prove that every that this polynomial is multilinear. But that's easy to see, right? Because the degree of so here is the only part where xi's are multiplied, and the degree of every xi is 1 because every xi appears exactly once, either over here or over here, right? So this polynomial is also multilinear. Yeah, so let's go back to the second question. Prove that every function is multilinear polynomial. So the polynomial that we saw over here was over f2. Now we are doing this over arbitrary field, FQ. Okay, so the construction would be analogous. So if you look at this construction, you could have written this as sum over b in 0, comma 1 to the n, f of b times this term, right? I so I'm only doing this for f of b equals 1, but yeah, because for f of b equals 0, this is 0 times something which disappears, right? So you can directly use this to generalize the polynomial. So consider, so this should be Excel. Yeah, and the claim is so I had A in the previous book, so it will be here. Okay, so the crucial observation is actually made this observation in the previous proof as well, but let me make it over here. Observe that P of A is just f of A times. Okay, so when you plug in A over here, for let's look at all the B's over here, right? Corresponding to every B, you have a term over here. When you plug in A over here, as we saw in the previous problem, this term becomes 0 for every B not equals A, and this term survives for all only for B equals A, right? So uh, PA would just be this term where B equals A, so f of B becomes f of A, and product I and AI equals 0, 1 minus AI, which is 1, which is just f of A times 1 is equal to f of A. Yeah, so this proves the claim, and yeah, again, the polynomial is multilinear because every xi appears either here or here, so its individual degree in any monomial is at most 1. Okay, now give me a second. Okay, so now let's look at the third problem. Okay, so in the class, we saw how to construct a polynomial of low degree that approximates or over F2. Now what we'll see is how to construct this over any FQ. Oh, my laptop battery is running. Oh, let me connect my charger. Yeah, uh, fine. Yeah, so now we'll see how to do this over any FQ. Okay, so actually, yeah, let me just do this with square. Actually, no, let's keep it at the degree should be, and the error should be. Okay. So again, this construction would be a straightforward generalization of the construction we saw in class. Okay, so let me first give you the construction, then I'll prove that it works. So uh, subsets of n can be I for all I every x j. Okay, let me know for every j in n, and sorry, for every j in t. Probability that xi in Sj is half, and uh, half, and this is independent of everything else. Yeah, so the way we pick S1 to St is by just going over all the variables, and every variable xi is in Sj with probably half, it's not in xi with probably half, and all these events are independent. Okay. So now let P So this is our polynomial. Yeah, and if you look at this, this is very similar to what we did in the class. So in the class, we were working over F3, and so this was Q. So now we are working over FQ, so this is Q minus 1. Okay, so now what we'll prove is this. For all, yeah, so we'll prove that this is true with or divided minus t to the minus t, so there is at most with the minus t. Yeah, before I forgot, I also need to look at the degree of this, right? Yes, with the degree of, so the degree of p is, okay, so uh, the degree of this term is q minus 1, and we are multiplying this t times. So the degree of this entire thing is also q minus 1, and then we are multiplying it t times, right? So the degree is q minus 1 times t. So the degree is fine. Now let's look at the error. Yeah. So the proof of this, okay, to prove this lemma, we'll use some facts. So first, the fact we'll use is called Fermat's little Fem- Fermat's little theorem, or FLT for short. So Fermat's little theorem states that for any alpha in FQ, alpha to the Q minus alpha is equals to 0 mod Q. And one way to see this is the following. So it's to realize that, okay, so for alpha equals 0, this is clearly true, right? And every element in FQ other than 0, that is 1 to up to Q minus 1, is a multiplicative group ZQ cross, right? Now the order of that group is Q minus 1. And we know that the order of any element in a group of, okay, so we, okay, so it's a group ZQ, right? ZQ cross, and we know that in any group G, A to the size of G is equal to 1. Where 1 is added into the group, right? So since ZQ is a group of order Q minus 1, for any alpha in ZQ, alpha to the Q minus 1 would be 1 mod Q. So alpha to the Q would be equal to alpha mod Q. And so alpha to the Q minus alpha would be 0 mod Q, right? So this is how you prove Fermat's theorem using the fact that for every element in the group, element to the order of the group is 1. Okay. And that you can prove using Lagrange's theorem that the subgroup, every subgroup of a group divides the size of every subgroup divides the size of the group. Now, pick any element alpha. The group generated by alpha is alpha, alpha square, alpha cube, and so on. Let's say its order is k, so alpha to the k is 1, but then k must divide q minus 1, which means the alpha to the q minus 1 is 1. So basically, what I quickly sketched over here was that you can prove Fermat's little theorem using Lagrange's theorem that every subgroup, the order of every subgroup divides the order of the group. Okay, you can try this on your own, and if you still have doubts, you can ask me in the forum or in the next session. Okay, yeah. So using this, let's see how to prove the lemma. So to prove the lemma, we'll prove two claims. Uh, the first claim is that if okay, let me make it little more explicit. For all x in yeah, it's the proof of this part is fairly simple. So if the OR is zero, if the OR is equal, okay, if OR is zero, then every xi is zero. And so let me just copy it. Ah, oh, this should be I in N. This should be I in S J xi in S. Yeah. Okay, so all of these are zero, which means all this is one. And so this product is one because every individual term is one, and so this is zero, right? So with probability of one. So here there is no bad case. Here the function is all the polynomial is always correct. Now let's look at um, okay. So how do we prove this? So again, the proof is similar to something that we saw in class. So we want to uh, lower bound the probability that Pi is one. So we'll upper bound the probability that P of x is zero. So when will P of x be zero? P of x will be zero if this is one, which means each and every one of these product is one, right? So this is probability that, yeah, let me copy it again. Great. Or let me change this. For origin T, this is 0. But this is the same. So if this is 0, which means this is 1. Okay, so now we'll use Fermat's theorem and replace sum over ixi in sj xi to the q minus 1 by, okay, oh, yeah, I should have written here the form. Okay, fine. So from Fermat's theorem, when alpha is not 0, what do we get? When alpha is not 0, we can cancel alpha out and get, okay, so let me finish. You can do some this, right? So now we know that alpha is not 0, so alpha to the q minus 1 must be 0, right? So alpha to the q minus 1 is congruent to 1 mod q. Okay, so this tells us that this can't be 0, because if this were 0, if this sum were 0, then to the power q minus 1, it would become still be 0. And this, since this is 1, this tells us that sum is non-zero. So we get that probability. By the way, over here I'm using FLT. Yes. So probability, oh wait, messed up. So we want this to be 0. So we want each of these to be 1. This is 1. So this is 0. So yeah. Okay. So now let's use FLT. So suppose this were non-zero, right? So let me call this alpha. Okay, alpha to the q minus 1 is 0. So multiply by alpha on both sides, I get alpha to the q is equal to 0 mod q. But we know that alpha to the q is equal to alpha mod, right? So which tells us that alpha must be 0. So this tells us that this must be 0. Still, I should write a mod q everywhere. Okay. Yeah. Okay, so now, uh, yeah, so this is equal to probability, sorry, product. Why should I write using FLT? Okay, just give me a second. Okay, okay, so this is, yeah, so since the OR is non-zero, there exists at least one J. Okay, I messed up my indices. Should be I star. Exists. Yeah. So since yeah, so since yeah, the OR is one, there must exist an xi star which is one, and this happens when that xi star is not in Sj, but that happens in probability half because every xi is in Sj probability half, right? And this is one, two, three. So this gives us the desired bound on the error. So is this fine? Okay, so let's look at the next topic. 0 should map to 1. Yeah, so we have a polynomial from 0, comma 1 to 0, comma 1. And we want to convert this into an equivalent polynomial from minus 1, comma 1 to the end to minus 1, comma 1. We saw something like this in class, but let's see this more explicitly. Yeah, just a second. Yeah. So let the so we want to construct Q, right? Okay, so now when okay, so we want to construct Q, and what do we want to do? So 0 must map to 1, and 1 must map to minus 1, right? So when the input to let's say when the input x1 to P is 0, the input y1 to Q must be 1, and when the input x1 to P must is 1, y1 must be minus 1, right? So when so yi is, I mean, you can think of yi as a Boolean function in xi, right? Okay, so you can think of yi as a function in xi over, let's say, minus 1, 0, 1, right? And we saw how to convert a Boolean function into polynomial. So over here, applying that would look like 1 minus xi times 1 plus xi times minus 1. So this is, okay. And so xi is equal to, okay, now consider, okay, yeah, let me just call it R. Okay, so let's look at R. So, okay, so let's say yi is 0. So, okay, so we are interested in creating a polynomial of plus minus 1, right? So let's say yi is 1. In that case, this is 0. And when yi is 0, Okay, when yi is 1, this is 0, and yi is minus 1, this is 2 over 2, this is 1, right? So, what do we get is this, then for all r of y is p of, uh, okay, how do I write it? Yeah. So, R is R is making progress toward constructing Q, because now what we have done is we have taken in an input in minus 1 comma 1 to the n, mapped it to an input in 0 comma 1 to the n, and the output of R is the value. So the output of R at y is the value of P at the corresponding string, right? So it's in 0 comma 1. Now all we have to do is take this uh, 0 comma 1 and map it to plus minus 1, and we would be done, right? Because then the output of R would be plus or minus 1, depending on whether the output of the corresponding string, output of P at the corresponding string is 1 or 0, right? So, okay, so we can set Q of 1 minus. Okay, so what do we want? When R is 1, sorry, when R is 0, we want Q to be 1, and when R is 1, we want Q to be minus 1, right? Why is the I over here? Yeah. So this is a desired polynomial. Why? Because, okay, suppose you plug in the all one string, then that would become over here all zeros. And then suppose that the value of the function, value of p, the polynomial was 0, then you would get 1. And if the value of p were 1, you would get minus 1, right? Similarly, when you were to plug in, let's say, the all one string, you would get all zeros over here. And again, if the value of p was 1, you would get minus 1. If the value of p was 0, you would get 1, right? So what's happening is you take a string over here, it's this maps it to the corresponding string, and this whole thing maps the output of p to the corresponding output of p is 0 or 1 to 1 bar minus 1. So we are going from uh, minus 1 comma 1 to the end to then using p to go to 0 comma 1, and then again going back. Yeah, this is what's happening. So I hope this is fine. So let's look at the next problem. Yeah, so in the class, to prove that no low degree polynomial can approximate parity, we used an approximation, an upper bound on a certain sum of certain binomial coefficients, right? So now we'll prove that. So show that. Why should I take it? Let's say 2 over 3 times 2 to the n. The constant 2 or 3 doesn't matter. It can be like 1 plus any constant, sorry, 1 over 2 plus any constant, and this would work. I'm just using 2 or 3 for simplicity. Okay, so let's split the sum. Now this is 2 to the n minus 1. Why? Because, oh, this should be 0. Yeah, yeah. Why? Because sum over I in 0 to n and choose I is 2 to the n because this is 1 plus 1 to the n, right? So if you take the binomial expansion of 1 plus 1 to the n, which is 2 to the n, you would get this. And if you like split this at n over 2, you get exactly half over here, right? So the half should be 2 to the n minus. So the entire thing is 2 to the n, so the half of it should be 2 to the n minus n over 2, which is 2 to the n minus 1. Okay, okay, wait. Should this be n over 2 or n minus 2? N over 2 minus 1. Okay, 0 matches with n. Actually, I think this should be maybe minus in the other case. Yeah, I think it's minus 1 because so 0 and n are the same, 1 and n minus 1 are the same. Yeah, so the sum from I equal to 0 to n over 2 minus 1 plus n over 2 plus sum from n over 2 plus 1 to 2 to the n, that would be 2 to the n. And so the sum of I equals to 0 to n over 2 minus 1 plus sum over I equals to n over 2 plus 1 to n. That would be 2 to the n. 2 will be at most 2 to the n, and so the first half would be 2 to the n minus 1. Yeah, right. And let's look at the second part. Plus, okay, let me split this further. Let me split the second part further. Okay, okay, we should level it first. Okay, do I just do it like split it like this, or I can get? Oh no, no, no! What am I doing? I can get away with something much easier. Yeah, I don't just split it. Okay, so let me keep this sum as it is. Okay, so now what I can do is I can write this as 2 to the n minus 1. Okay, okay, now this sum I need is okay. So what does do I want to split? Okay, let me not split. Okay, so now we know that uh, I equals to n over 2 minus root n to n because mm, n choose k is the same as n choose n minus k. Yeah, so when I put I equals n over 2, I get n over 2, n over 2 plus root n, I get root over, yeah, so I get this. Okay, now we also know that up to n over 2, the binomial coefficients increase and then they decrease, right? So I can write this as root n times uh, n choose n over 2. Are there root n terms or root n plus 1 terms? So minus root n to 0. Yeah, there are root n plus 1 terms. Yeah, okay. So this is level first. Yeah. Okay, so now I can write this as so from Stirling's approximation, we have this. What is this? So this is, oh wait, I should use something better. Yeah, I'll have to use something better. Yeah, I think I have to use the exact approximation. Okay, no, 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 that. Okay, so let me call this fun. Wait one more. Okay, so it's n minus 2. So 1 plus, okay, so it's 1, 2 times, 2 times. You missed. This is yeah. Okay, let me work this out offline. And I can like write this down and upload it in the notes. Yeah, I'm wasting too much time. Sure. Give me. Yeah. Oh, okay. So, that's all I have for this week's video. Let's look at uh, this year's week 7 assignment. So the first problem is which of the following is not a monotone function? XOR, majority, and or. And the answer is XOR. So let's see if I. Okay, what happened? Okay, yeah. So, okay, I can just write that 50 minutes, right? So X, Y. Yes, this is 0, this is 0, this is 1, this is 1. Now over here they flip the 0 to a 1, but this goes down, right? So this is less than equals to this, but this is less than equals to this. This is not monotone. What about majority? So actually, okay, yeah. Let me, instead of just doing it for two, let me do this for n variables. Okay. So because uh, okay, 0 x XOR 1. So 1 XOR 0, all zeros. Okay, let me write it like this. This would be, this is 1, but XOR of all ones is 0 whenever, whenever n is even, and XOR of okay, yeah, I can get rid of this case. It's, let me write it like this. Yeah, so XOR of 1 followed by all zeros is 1, but XOR of 1 followed by all zeros is 0, even though this is the largest string, so this is not monotone. Is monotone. Why? Because majority of x1 to xn is equal to 1 implies sum over I in 1 xi is at least n over 2 implies sum over and this implies that is equal to 1. Yeah. So whenever majority of x is 1, majority of y is 1, if y is greater than equals to x, so this is monotone. What about C? Yeah, so and of, yes, and is also monotone. Yeah, so everything other than XOR is monotone. So now let's look at the next problem. So the next problem is consider the undirected graph G with four vertices and this adjacency matrix. And what is the value of clique 4, comma 2 and 3, comma 4 respectively? Let's first draw the graph. Okay, so one has edges with 2 and 4. Uh, 2 has edges with 1 and 3. 3 has edges with 2 and 4. And 4 has edges with 1 and 3. Okay, so this is the graph. Now, clique 2, comma 4 is 1 if there exists a clique of size 2. So, since say 1, comma 2 is a clique, this is 1. Okay, however, there is no clique of size 3, right? Because, yeah, 1, 2, and 3 does not form a clique. 1, 2, and 4 does not form a clique. And 2, 3, and 4 also does not form a clique. So, yeah. So it's 1, comma 0, option C. Let's look at the next problem. So which of the following collections of sets is a sunflower? Okay, so this needs to be worked out. So let's look at all the options. Okay, so one. Okay, so let me call these sets A, B, S1, S2, S3, S3. Okay, let me call the sets. If Z4 exists, it doesn't see. Okay, so for one, so when does Z1, Z2, Z3 set for a sunflower? When the intersection of every set is the same, right? So Z1 intersection Z2 is 1, 4, yeah, 1 and 4. Z2 intersection Z3 is also 1 and 4. And Z3 intersection Z1 is also 1 and 4. Yeah. So A is a sunflower. What about B? Z1 intersection Z2 is 146 and Z2 intersection Z3 is 1 and 4. So this is not a sunflower because the two intersections are different. Yeah, so because of this, this is also not a sunflower. Yeah, so this is the, again not a sunflower. So only A is a sunflower. Now let's look at the next problem. So the next problem is let Z be the collection of sets of size at most, where the size of each set is at most L. Then according to the sunflower theorem, Z is guaranteed to contain a sunflower with P petals if the number of sets in Z is greater than for the largest possible value. P minus 1 to the L, P to the L times L factorial, or P to the P minus 1 to the L times L factorial. So what's the answer? Well, it's P. We saw this in class, so I won't do this again. Yeah. Now let's look at the next problem. Give this. Yeah. So let's look at 5. So let F and G be the approximators to the input of an OR gate. C is the clique indicator function. Xi and yi are vertex subsets of the graph G. F, this symbol G, is the approximator of the OR gate, then which of the following is true? F UG must be 0 when F or G is 0. F UG must be 1 when F or G is 1. F UG must be 0 when F or G is 1. And F UG may be 1 when F or G is 0. So let's look at this. Okay, so how is FUG constructed? So you have electrics. by plucking the sunflower, right? Yeah. Okay, so now suppose 11 first do one. Then so if CXI, so otherwise, what's the only way that these CXI or CYJ would be removed? It's if they are removed by plucking the sunflower, right? Otherwise, they're sorry, yeah, yes. But in that case, so a subset of a clique is a clique, right? Uh, yeah, so whenever F or G is 1, F U G should also be 1. So Q G may be 0. No, no, this is true. And D is, yeah, so this is true. Yeah. So F U G may be 0 when, so this contradicts this. So this can't be true. Now we need to look between A and B. Okay. So, and uh, for all I comma j, oh, they should be extensively. Yeah. So, but while plucking the sunflower, we might introduce a clique, right? For example, let's say that like you have a few petals. The petals are not cliques, but their intersection might have a clique, right? So, Yeah, so this means A is false and D is true. Okay, so now let's look at the next one. So it's similar but for the AND gate. So let F and G be the approximators to the input of an AND gate, and C is the click indicator function. Xi and Yi are vertex subsets of the graph. F uh, and G is the approximator of the AND gate, then which of the following is true? F is called F join. Yeah, yeah. F join G must be 0 when F and G is 0. F join G must be 1 when F and G is 1. F join G must be 0 when F and G is 1. And F join G may be 1 when F and G is 1. So let's look at this. Okay, so here's how F and G is constructed. Okay, so if F and G is this. From this, we write this as or I or J. So let me call this step 1. Excuse me. Yeah, so this is the first step. Then in the second step, we so this is step 2. Okay, so now let's look at the case when so when then what does this mean for all I? So however, yeah, so when f and g is 0, f join g might be 1, maybe 1 when this is 0, this is true, and yeah, a and d are contradictory, so a is false. Now let's look at the other thing. However, yes, the second step can, like, so, oh, sorry, the first step can destroy cliques. So, F showing G may be zero. Yeah, C is correct. So now let's look at the problem 7. So this two we have seen in class. So let F and G be the approximators of the input of an AND gate. C is a clique indicator function for cliques of size k. X's and Yi's are vertex subsets of graph G. F join G is the approximate of the AND gate, and F and G doesn't equals to F join G fails for at most how many positive test graphs. So this we saw in class is A. And for the next problem, so let F e and G be the approximators of the input AND gate. C is the clique indicator function for cliques of size k. X is and Y is the vertex subset of the graph G. F join G is the approximator of the AND gate. Oh, I think this should be, is for at most how many negative test graphs. And this we saw in the class is, yeah, this. Oh, yeah, so that's all the questions I have for today. We can end the meeting and meet next time. Bye. Thanks.